All right, so before we get into the mechanics of how colors mix, we've got to establish an understanding of how we perceive color in the first place. Color is, at the end of the day, a sensation, something that we feel in a way. And that means that the feeling is usually stimulated by something, and usually that stimulus is light. Light is just our word for electromagnetic radiant energy that we can see, and that energy has different properties. So this is a model of a photon, a kind of quantum or packet of electromagnetic radiation. It's two interlocked wiggles, an electric wiggle and a magnetic wiggle. You can see that we could describe the wiggle packet in different ways, like what direction is it flying, or how lined up or not are the two wiggles, or are the wiggles leaning one way or another, or how high are the bumps on the wiggles, or how far apart are the bumps on the wiggles. And when we're studying color, actually, that last question is the really important one. How far apart are the bumps on the wiggles? If I measure from one peak of the wave to the next peak of the wave, that distance, that's called wavelength. And EM wavelengths actually could be measured with this ruler, like some radio waves are that long. But the visible light wavelengths are much, much smaller. They're measured in nanometers, billionths of a meter. Here's the wavelength range of visible light, about 400 nanometers long to about as long as 700 nanometers. And when you turn on a light, you're suddenly bathing in wiggles. And what you're seeing is all the wiggles with wavelengths between 400 and 700 nanometers. How many of each do you figure there are? Well, I mean, we could count them. We could make a bar chart. Let's see. Well, here's the stack of how many wiggles at 503 nanometers. And here's how many at 612, and so on and so on. You fill it up, and you get this graph that shows us not just how much light is coming out of that bulb, but how much light at each wavelength. You notice something about the graph for this light? It's not even. There's a little more at this end than at this end. That means this incandescent bulb has more power in the longer wavelengths than in the shorter ones. Let's try a different light. This fluorescent one. Now look at that. There's like weird bumps in the graph. There's certain wavelengths we have a lot more of. Well, how about a light modeled on the sun? Oh, that's bright. And it's pretty different, too. What you're seeing is that different light sources, different illuminants, as color scientists call them, have different compositions. And because our sensation of color usually begins with light, the composition of the light or illuminant can influence the colors we see. Take a look at these patches of color. Under sunlight, under fluorescent light, under incandescent light, and for an extreme example, under monochromatic red light. The colors look different under different illuminants. The illuminant isn't the only part of the color equation, though. Let's run through the rest real quick. So you remember the graph of the illuminant's power at all the different wavelengths? Well, the object that light is hitting could scatter it all back, and then we would see that object as white. But the object can also modify that graph. A red object is going to absorb all the short and medium wavelengths and only reflect the longer ones. A yellow object only absorbs the short wavelengths, and a green one reflects only the middle wavelengths. And we'll get more in depth on all that later. So now we have the illuminant and the object. But we should also consider the context that the light and the object are inhabiting. The situation can affect the appearance of a color in a number of ways. Think about pollution, smoke, haze, what happens to color underwater. And the size of an object can affect our perception of its color. Where an object is compared to other objects can too. Finally, understanding how color works means thinking about the observer. That could be a human or a camera or a bumblebee. It could be somebody with color blindness or cataracts. Or think about how colors might look different based on your age or your hormonal balance or how you might be influenced by memory. Some languages have more than one word for blue. Some don't have a separate word for blue and green. It doesn't mean those people can't see the difference, but it affects how they categorize and remember colors. Studies have shown that. Anyway, the point is, if you're asking what color is it, it matters who you're asking. To sum up, these are the parts of the color equation: the light, the object, the context, and the observer. You might think that without all four of these, we couldn't have color. I mean, that's one way of looking at it, but I want to emphasize something. You don't necessarily need an object to reflect light. You can see color directly from a light source. And you don't exactly have to think about the contextual factors to understand how color works. And actually, you don't even need light to experience color. I mean, there are hallucinations and synesthesia. So this is what I'm trying to emphasize here. If we're asking where exactly does color happen, it's not here or here or here, but here, in the mind of the observer. That's it for this lesson. Be sure to tune in for part 2 of how color works. We're going to talk about how the eye and brain turn light into color. And in the meantime, if you have any questions or want to chat, hop into the Discord. If you're from TikTok, you're invited to. Just remember not to share this link with anybody because, after all, you paid good money for it. See you next time. So how does the eye turn the light that enters into it into a sensation of color? Understanding this is fundamental to a deep understanding of how colors mix. Different light sources or illuminants have different compositions of wavelengths, and mostly if that mixed up soup of photons is somewhat even across the board, a balance of different wavelength photons, we've evolved to perceive that as white light. And if it's a little imbalanced, our eyes can adjust. But what if it's not balanced at all? Our eyes also evolved what we think of as color vision, but what you could also describe as wavelength imbalance detection. I'm going to grab some graph paper to help us visualize how this works, and I highly encourage you to grab some graph paper too and do this exercise as well. Let's fill a 7x7 grid with letters A through L randomly. I'm just going to go through in alphabetical order, but jump around in terms of where I'm putting the letters. That means I'll go through A through L 4 times and have one extra. So each letter represents a photon. Let's say the closer to A, the more energy the photon has, and thus the shorter wavelength. A and B photons are high energy ultraviolet photons, which are invisible, so I'm blacking them out. The closer it is to L, the less energy the photon has, and so K and L are infrared photons, which are also invisible to us, so let's black those out. My square of graph paper represents the light beaming out of a light source with equal power across the spectrum. It's got balance, or the same amount of photons represented at every wavelength. That means we won't perceive that light as having any particular color. Why? Remember, because you can describe color as wavelength imbalance detection, and this light source is completely balanced. But if my light source hits a yellow object, like this block, the shortest wavelengths are going to get absorbed, and all the other wavelengths are going to bounce off, and some will reach our eye. We detect that imbalance, that lack of short wavelengths. Okay, to simulate this absorption of short wavelength photons, I'm going to punch out all the highest energy ones, the ones the yellow block's absorbing. Those are the squares with letters A, B, C, D, and a couple of the E squares for good measure. Now, if we count up how many squares we have left with each letter, we can make a bar chart to display that count. This graph is a basic version of a spectral reflectance graph, and it shows how many photons of each wavelength are reflected to our eye from the yellow block. So this is important. This is the information that's coming to our eyes, but our eyes don't detect these graphs. We don't have a full range of detectors to get all these photon counts. Our eyes have only 3 input channels for daylight vision, not 8 or more like this bar chart suggests. So how does our eye compress all of this information into 3 channels? We have three types of sensors for daylight vision. Cone cells, called long, medium, and short. Each gathers a different range of photon wavelengths, and those ranges overlap. Now let's study this graph, which is a simplified version of how each cone type responds to photons across the spectrum. Let's imagine each of our three sensors has three possible responses at each wavelength: 0, half, and full sensitivity. The sensor missed that wavelength, half saw it, or totally saw it. So for example, at wavelength E, our long cone has 0 sensitivity, our medium cone has half sensitivity, and our short cone has full sensitivity. Make sense? Let's look at another example. At wavelength H, our L cone has full sensitivity, our M cone has half sensitivity, and our S cone has 0 sensitivity. Light with a wavelength of K is invisible to us. Why? Because L is at 0, M is at 0, and S is at 0. All three of our sensors aren't responding, therefore we can't see that light. So if this whole thing isn't making sense yet, pause the video. Compare the sensitivities of the three sensors represented by the three lines, the blue, the red, and the green lines. Look at how they're each responding to each letter, just to get that concept. Because now we're going to do a little math to understand how those overlapping ranges of sensitivity work together to turn imbalances of wavelength into sensation of color. Here's the reflectance spectrum of our yellow block again. Remember, the block absorbed the shorter wavelengths and reflected these longer wavelengths to our eye. But our eye compresses that information through these sensors with their overlapping sensitivities. So we'll multiply the number of photons at each wavelength by the sensitivity factor of each cone at each wavelength, and then sum up those numbers. Okay, so if we add these numbers together, we get the total stimulation for the S cone. If we add these numbers together, we get the total stimulation for the M cone. And if we add these numbers together, we get the total stimulation for the L cone. This combination of three numbers is what our brain happens to interpret as the color yellow. At least in this simplified version of how this works. I want to make a point here. Each sensor doesn't know the difference between the wavelengths it's detecting. It only knows how much it's being stimulated overall by the range it's sensitive to. This is why it's not sensible to label a certain wavelength of light as having a color. Wavelengths don't have color. Imbalances of wavelengths cause the sensation of color. And if you understand that, it allows you to understand how color mixing works. Listen, I so appreciate you coming along for this color theory ride. Thanks again. And I'll catch you next time for part 3 of how color works. In this lesson, we're going to build on what we did in the last video to better understand how light gets turned into a sensation of color. So let's look at those cone cell sensitivities again. Remember, this graph is a simplification of the reality, but a useful one. It's saying that the S cone is half sensitive to this wavelength, fully sensitive here, and half sensitive to this wavelength. The M and L cones have similar spreads of sensitivity, but at longer wavelengths. So a graph of light wavelengths coming to the eye, like this one, gets multiplied by the sensitivity factors of each sensor. Those numbers get summed up, and our eye sensors spit out these three numbers. Let's think about this for a bit. What's the smallest amount of stimulation that all three sensors together could receive? The smallest number the S cone could perceive would be 0, the M cone 0, the L cone 0. 0, 0, 0. Zero stimulation across the board is perceived as black. What's the largest number that the S cone could produce? Well, if we go back to our graph paper light source we set up last time, remember that the highest amount of photons of any letter was 4. We take 4 times a half plus 4 plus 4 plus 4 times a half. So add that all together, and the most we can get out of the S cone is 12. For the M cone, what's the largest number? Again, it's 12. And for the L cone, what's the largest number? 16.
This gives us a maximum stimulation, all three cones maxed out with 12, 12, 16, which we would perceive as white. Now, let's consider what happens when I max out only one of the three receptors. Say the S cone is at 12, and somehow those E and F photons didn't stimulate the M and L cones. We get this set of numbers, 12, 0, and 0. What color would that be? Who knows? Theoretically, it would be the most vivid possible indigo imaginable. But in reality, the most imbalance possible here would be stimulated by a spectrum that cut off at D, right? If we don't want to stimulate these other two cones, which means that the S cone would only be giving a signal of 2 plus 4 in this situation, or 6. This then is our actual purest blue sensation, the deep indigo you can see coming out of a prism. Let's consider the M cone in the same way. Theoretically, we could max out its signal at 12, and we could get 0, 12, 0, which would give us the most vivid green imaginable. But in reality, the overlap in sensitivities means that a pure M cone response is impossible. Well, at least for now, since we don't know how to hack our biology yet. With M maxed out, S would be seeing 6, and L would be seeing 10. That then is our experience of the actual purest green that we can see. Continuing this thought experiment with the L cone maxed out at 16, we'd get an impossibly vivid scarlet red, but with L fully lit up in reality, S is still reading 2, and M is still reading 10. Like with the S cone, though, the L cone can be stimulated in isolation. If the spectrum it was detecting only included I and J wavelengths, then the total reading would only be 6 out of a possible 16, but this is our real-life most vivid scarlet red. I hope this is making clear how important it is to the structure of our color vision that these sensitivities overlap. I can take those three numbers, the short cone, medium cone, and long cone numbers, and I can use them as three axes in a three-dimensional space, right? I can turn them into length, width, and height, and this gives me the beginnings of a box, right? I've got this one corner here with 3 rays coming out of it. The corner where all 3 cone cells are giving me 0, we perceive that as black. The opposite corner where all 3 cone cells are maxed out, well, if they're all fully stimulated, I'm perceiving white. So that's the opposite corner of this cube. The other corners of the box are kind of impossible to reach because you can't max out only one sensor with the other 2 staying at 0. What if we could see these colors? Well, the way our eyes are wired to our brain, the maximum S would encode a super blue, the maximum M would encode a super green, and the maximum L would encode a super red, you know, theoretically.
As you probably figured out by now, we are working our way towards 3-dimensional models of color that will help us talk about how additive and subtractive mixing work. So far, we've been in the LMS space, or a very kind of limited pedagogical version of the LMS space. This is a space that color scientists use as a basis, but usually they go from there to construct something based on perceptual dimensions, or if you're a computer color person, you translate it to RGB, which is where we will pick up next time. We've seen that all the possible combinations of visible photons that reach our eye get filtered through our 3 sensor types and turned into a set of 3 numbers, which our brain then interprets as a color. If we plotted out all the number combinations, even the impossible ones, we'd get something like a cube. And with that in mind, we're going to use a cube as our model for additive mixing. And for the time being, let's forget the numbers we were using before from the graph paper and the Tristimulus Theory Simplified worksheet. 12, 12, and 16 were our big numbers that things could add up to. We're going to be using this model, where everything is either 0, 1, 2, or 3. So let's start again with defining the corners of this cube of color. We start with the extremes. Black, where all 3 receptors receive no stimulation, is 0, 0, 0 in the center there, and white is 3, 3, 3. In other words, all 3 receptors are cranked up as high as they go.
Dark gray would be 1, 1, 1, and light gray is 2, 2, 2. Notice that all these have to go in the center of this diagram because we're looking from the top down on our cube at the moment, and these are all balances of stimulation. Remember, in an earlier video, I defined color as the result of our eye's wavelength imbalance detection system. And this is what this diagram is actually showing us. Balance means no hue, no chroma. In other words, there's no color information other than light or dark. So all shades of gray, black, and white go to the center of this diagram. And the further out we go, the more vivid the color is going to be. Let's do the math. Last time we explored 3 of the corners, maximum S, maximum M, and maximum L cone stimulation. Remember, these are impossible colors because the other 2 sensors can't be reading 0 when 1 is reading maximum. So what's the closest we can get? Well, those colors happen to be 3 colors which were theorized by Palmer, Wunsch, Young, and others in the late 18th century, and confirmed by James Clerk Maxwell and Hermann von Helmholtz in their experiments in the 1850s and 60s. Those colors are a deep scarlet red, an emerald green, and a luscious blue violet. So if a light spectrum increases in stimulating only the S cone, or only the M cone, or only the L cone, you get brighter and brighter blue, green, or red. You may have heard before that these are the additive primary colors, but now hopefully you understand why. All right, say we've maxed out the S cone, we've got blue, but now we start adding M cone stimulation. A little bit, and then a little more, and then we max out the M cone. With both S and M maxed out, we end up here, this corner. Here's a review question. Is it possible for a light spectrum to produce a cone cell reading where S and M are maxed out but L is 0? No, because the M and L cones overlap so much that you can't max out M without also stimulating L. So what we're seeing here is the highest possible imbalance in favor of the short and medium cone and against the L cone. The spectrum that produces this color would have to be a spectrum that cut off around E or F on our chart from last class, or around 500 nanometers or so. Such a spectrum is possible to see if you look through a prism at a black and white figure like this. This area is that purest possible S plus M color. This is the color we call cyan. Okay, now let's keep moving by removing a little S-cone stimulation and then removing a little more, and we arrive back at green. And we can keep going around the perimeter if we start adding L-cone stimulation, right? That causes our green to appear yellower and then yellower until we get to yellow at this corner. Can a light spectrum produce this kind of imbalance where M and L are maxed out and S is at 0? No, but we can get close, and this is the color yellow. And coincidentally, we can see that purest version of that through a prism the same way we saw cyan, but on the opposite side. We keep moving around the perimeter by now removing M-cone stimulation until we get to red. And then how do we keep going? Well, we have to now add S-cone stimulation little by little until we get a very interesting color, magenta. Again, it's impossible to max out short and long cones with 0 stimulation to M, but the closest we can get is a spectrum where the whole middle range is blocked out. And this kind of spectrum can be created with a prism if you put a thin piece of tape along the middle and shine the sun through it. Okay, we finish up by gradually removing the L cone stimulation until we come back to blue, and now we have something called the hue circuit, the ring of highest saturation colors, the most vivid colors we can see. If I write in our coordinates, our SML coordinates, you can see the beautiful symmetry of these 6 colors at the corners. They're all just different combinations of 0 and 3. In other words, of which cone cells are being maximally or minimally stimulated. Before I close the first section of this course, I want to point out that making a cube out of the 3 cone signals, like we've been doing, doesn't tell the whole story of color. There's a lot more to it, which is why so many other shapes have been proposed as the model of the color solid, like the
the sphere, the pyramid, the double cone, even crazier things like a rhombohedron, a cuboctahedron, a zonohedron. Why? Because we're measuring color relationships based on perceptual differences that our brain is interpreting from the input that our eyes are sending. And we have to decide what those perceptual dimensions are. For artists and designers, those dimensions have traditionally been hue, lightness, and chroma. Sometimes other measures like saturation, brilliance, and blackness can be useful. And sometimes it makes the most sense just to go with the 3 purest possible single cone stimulations as the corners of our cube. From here, that's what we'll do as we get into additive mixing. The purest single cone stimulations, that's what some people would call the additive primaries. That concludes the first part of our course, How Color Works. I know you'll have follow-up questions, so please drop them in the Discord. Do not adjust your television set. I'm in black and white right now because I want to show you something. This is a nifty gadget where I can control the amount of red light with this dial, the amount of green light with this dial, and the amount of blue light with this dial. It projects 3 beams so they can overlap and you can assess how they mix. In black and white, though, we're forced to focus on only one kind of difference that emerges as the beams overlap, a difference in brightness. Here, my red light is turned up. Now I'm going to slowly add more and more green light. Where the green and red light overlap, the area gets brighter. Why? More light is falling on the same spot. Let's say these 2 lights are both cranking out the same number of photons per square inch. In this spot, then, there are twice as many photons per square inch hitting the wall and reflecting back to your eye. We're going to perceive that as brighter. Here's my green light and my blue light both cranked up. Again, the overlapping area is brighter because roughly twice as much light is bouncing off this area as is bouncing off these 2 areas. If I overlap all 3 lights, I get an even brighter patch in the middle because this area is reflecting photons from all 3 lights, right? By ignoring color for a moment, this nicely demonstrates the basic truth about additive mixing. What we're adding is light. That's all pretty straightforward, but where it starts to mystify us to seem a little bit like magic is when red and green combine to make yellow. The question is, when we overlap different colored lights, why does the hue change? This red light is probably a narrow band of wavelengths with a peak of around 635 nanometers, or I on our simplified chart. On the chart, you see that the only cone sensitive to I is the L cone. So if I turn it up or down, my L cones are getting more or less stimulus, but the M and S cones are unbothered. This green light has a wider band of emission. Maybe it peaks around 540 nanometers in the middle of the visible spectrum, or F on this chart, but it's also giving off some E and G. That's going to light up all 3 cone types. See, the L, M, and S cones all have some sensitivity overlap in the EFG range, but the M cone is going to dominate that mix. Finally, the blue light is emitting a narrow band that peaks around 450 nanometers. That's D on our simplified chart, and notice that only the S cone is sensitive to that light. Well, let's start adding a little bit of 540 nanometer light. You'll see that in the overlap, as we noticed before, the light gets brighter. But the wonderful magic of additive mixing is that it also changes hue. In color science, there's an important concept, dominant wavelength. A spectrum's dominant wavelength isn't where the highest spike of photons is in its spectrum. It's more like an overall average of what wavelength imbalance we're detecting. So when I add 540 nanometer light, I'm shifting the average wavelength of the spectrum away from 450 nanometers. And more to the point, I'm shifting the balance of how my eye sensors are being stimulated. My M cone gets more involved, so the hue I experience shifts towards cyan. Let's gradually remove blue now. What's going to happen in my eye?
The S-cones are having less and less of an influence on the perception of the center area, since there are less and less photons for the S-cone to pick up. So the imbalance of stimulation is going to favor the M-cone more and more until the hue I experience in the middle shifts away from cyan toward green. When we start adding a little bit of this 635 nanometer light to my green, watch what happens. A little bit more. It starts to get a little chartreuse. There's a big spike in the middle from this, and a little bump in the long wavelengths. How is that chartreuse? Remember, we need to think in terms of dominant wavelength, which is a kind of average or mean wavelength of the spectrum we're looking at. The bump here shifts the average this way, and if I turn up the red, it shifts the average even further until we experience more of a yellow. So this is pretty cool. This spectrum with two bumps can look yellow. This spectrum, which is what the paint cadmium yellow reflects, can also look like yellow. So the structure of these two spectra are pretty different, but both are lighting up the M and L cones, and both are invisible to the S cone, which can't detect any of the wavelengths present in either spectra. So we've demonstrated that multiple different spectral imbalances can render the same cone cell response. Well, now we'll turn down the green and see if we can't get orange. Here we are. And then we find our way back to red. And now the real insanity begins. We start adding back some 450 nanometer light. Here we are. Look at the color in the overlap now. Ah, lovely. Let's pause on magenta for a second. We have to talk about dominant wavelength in regards to magenta because the concept kind of breaks down. In color science, you can't say a magenta has a dominant wavelength of X, because if you averaged it out, you'd end up in the middle of the spectrum, which is green. And this is a clue. It's a clue that our eyes aren't really averaging wavelength, they're triangulating stimulus. Dominant wavelength is just a convenient way to describe how many colors, not all, but many, relate to the spectra that can stimulate them. Many colors can sort of be labeled with their dominant wavelengths, but purples, hot pinks, and magentas, these colors can't. This doesn't mean purples don't physically exist. It's just a consequence of the fact that colors aren't actually wavelengths of light. Wavelengths aren't colors. Imbalanced spectra stimulate the sensation of colors. And that's why additive mixing of three monochromatic lights can even happen in the first place. Let's take one more tour around the RGB hue circuit to review, but this time I want to put a diffusion screen in front of this gadget so we don't see the overlapping circles and can focus on the hue of the overlap itself. At any given time as I go around the hue circuit, I'm only going to have one or two of these lights on, not all three. Why? Well, let's look at what happens if I do. If I add a third light, I'm adding a white component to the color. I'm increasing the brightness of the color, but decreasing its saturation. Saturation answers the question, how much whiteness is in the color? If there's no whiteness in the color, it's fully saturated. Here's a page from a Munsell Book of Color to illustrate what I mean. These four blues, even though they're getting darker and darker as I go down, aren't getting less saturated. This guy might have less chroma than this guy because there are fewer steps between it and gray over here, and it might be darker because it's closer to black, but it isn't any whiter than these guys. They all have the least amount of white possible for their respective lightness level. Back to my light mixing gadget. I've got a nice punchy blue here made of some 450 nanometer light, some 540 nanometer light, and as soon as I add in some 635 nanometer light, you see it starts losing saturation and getting whitish. So in RGB mixing, we can define the white component as the amount of the mix where all three monochromatic lights, red, green, and blue, are matching each other in intensity. Let's borrow a demonstration from Harald Kuppers to visualize this. His idea is that if you arrange the amount of red, green, and blue monochromatic light as a bar chart, you can scan sideways to add those primary lights into different amounts of 8 components. You can then imagine blending or averaging those components to get the resulting perceived color. So, say I have this much blue, this much green, and this much red. The amount to which all three overlap, this amount, adds up to white. That's our white component for this particular color. Now here's how much the green and the blue overlap, because the green goes this high, right? And blue plus green makes cyan. There's also a little bit of blue left over, which gives us this little bit of blue component. The blue is all the way up to the top of the scale. So there's no darkness here. There's no black component. Say I were to reduce the amount of blue light to something like this. Now we no longer have this blue component, and the cyan component has been reduced by about this much. Now there's a little bit of a green component, and also, because my scale goes up this high, there's got to be a little bit of a black component because all three of my primary lights are not at full power. So if I were to blur all four of these amounts of color together, I would have a grayish blue-green. Think of it this way. I've got this much black and white, so I've got gray. I've got more white than black, so I've got a light gray. And I've got a little bit more cyan than green. So I've got a color that leans towards cyan, but is between cyan and green in hue. Overall, that means it adds up to a grayish, cyanish green. Here's another example. You can see the amount of all three colors overlapping is quite small. So I'm going to reduce the amount of white to here. Green plus red in additive mixing is yellow. So I have this much yellow because that's how much my green and red are overlapping. And I've got red going to the top of the scale. So I've got this much red in my final color. So this much blue, this much green, and this much red is adding up to this much white, this much yellow, and this much red. I have a color that is between red and yellow, so it's orange in hue. There's a much bigger yellow component, so it's probably an amber or yellow-orange, leaning toward yellow. And it's also slightly desaturated. It's got a little bit of white mixed in. We can also work backwards. So here's a swatch of violet. We see that it's dark, but it's fairly saturated. So there may be a sizable black component, but little or no white component, because remember, saturation is related to how much white is in the color. And I feel like this is a pretty saturated color, but it's not like super vivid. I'm going to leave a little bit of green because that's how much of all three I would need to add up to this white. And now I'm going to figure how much red and blue do I have. Okay, so here's my guess. My guess is that there's a little bit of a black component. We've got a fairly dark color. We've got a lot of blue. We've got almost as much red. Those are adding up to magenta, and there's a little bit of blue remainder because I'm seeing this hue as leaning a little more toward violet than toward magenta. And then I don't think it's perfectly saturated, so I'm adding some green light so that all the three primary lights are adding up to this much white, and that's giving me a slightly grayish, bluish purple. I happen to have a hex code generated from this violet crayon. So let's look at the red, green, and blue components in a color picker and check my results. Interesting. I underestimated the green, meaning this color as a hex code is less saturated than I thought. The physical crayon color does look a bit more saturated than its RGB counterpart, though crayon and light are hard to fairly compare. One reason is that the gamut or range of possible colors is limited by the primary lights that generate it. But more on that in the next class. In this lesson, I want to get a little technical. I want to help you develop a basic understanding of how color displays, like the screen you're looking at right now, leverage additive mixing. I also want you to grasp a couple limitations inherent in mixing colors with light or pixels. Let's get into it. In the last lesson, I mentioned the range of colors that you can mix from lights depends on the lights you're using. We've been using this gadget, which contains 3 LEDs that emit photons within 3 narrow ranges of wavelength, peaking around 450 nanometers, 540 nanometers, and 635 nanometers. This guy is the 1931 chromaticity diagram. This figure is the result of a bunch of math, and it's a bit more advanced than the cube-like space we've been playing with. That was the LMS space, derived from how much stimulus each cone cell type is receiving. This model's flat because it's not really considering differences in lightness. The word chromaticity actually means a number representing the two aspects of a color that aren't lightness. It's hue and chroma. So different colors can have the same chromaticity, two colors with the same hue and chroma, but different lightnesses would have the same position in this diagram. It's also worth knowing that colors with different spectral compositions can have the same chromaticity too, like these two versions of yellow we talked about in lesson 5. So I guess the point of this diagram is this. It's trying to answer the question, how can we connect the physics and the psychology of color? The physics part is actually this curvy line. All the colors we could perceive from a monochromatic light source, a light source pumping out only one wavelength, lie along this line. At this end of the curve, only our S cone is stimulated. Then we move up, and the M cone gets more and more involved, and it curves this way, and the S cone gets less and less involved, and the L cone starts to get involved. It curves back down, and finally, down toward this end, only the L cone is involved in perceiving that monochromatic light. Since monochromatic colors can be stimulated by the most extreme wavelength imbalances possible, one wavelength cranked all the way up and all other wavelengths at zero, these colors along this line are associated with those wavelengths, which are therefore labeled along the curving line. That's why this is called the spectral locus, this line. All the colors along this line are the full saturation colors between blue and red, hot pink, magenta, purple, and it's called the line of purples. These hues are non-spectral hues. In other words, they're the hues that don't appear in the rainbow. So much for the edges. As we move toward the center, what we're doing is we're sort of mathematically predicting what color we'd perceive as the imbalances of wavelengths shift. Remember, our color vision is essentially wavelength imbalance detection. So a light source with equal balanced amounts of all visible wavelengths would be somewhere in the middle here, and that we would perceive as white. Balance, no color. Okay, so if we're talking about additive mixture, what can this diagram tell us? Well, let's start by figuring out where our three lights are. My blue LED is around 450 nanometers, here. My green LED is around 540 nanometers, but if you recall, my green light wasn't as pure. It was emitting a little bit of E and G, or the wavelengths to either side of its spike, so we'll pull the green in a bit. It isn't as saturated. And finally, my red LED was around 635 nanometers, here. Now we have three pins that make a triangle. And that triangle shows us how saturated all of our two light mixes can be. So for example, let's look at our red-green mixes. My oranges, yellows, and chartreuses are all pretty close to as saturated as they can be, pretty close to the spectral locus. Now look at the line of all my magentas and purples. Again, it's pretty close to as saturated as possible. However, there is this thin strip of purples beyond my triangle, right? That means if I used spectral lights closer to ultraviolet and infrared, closer to the edges of the visible spectrum, I could create slightly more saturated purples. However, they would also be darker because it would be made of two lights that I can barely see. Here's where it gets really interesting. Look at the line of all the mixtures I can make with my green and blue LEDs. Do you notice something? It's nowhere near the spectral locus. The blue-greens I can make are significantly less saturated than the blue-greens on the spectral locus. Put it another way, there's a lot more whiteness in the cyan I can make with my light mixing gadget. Say you wanted to mix better cyans using only 3 lights. Well, we could choose a green light with a much shorter wavelength. But then look what happens to my yellows. They get very desaturated. So it's a trade-off. Some displays have been invented with 4 primary lights to try and solve this problem. You get nice punchy cyans and nice deep yellows, but with 4 types of lights in your display, it becomes more expensive to manufacture, and those haven't really caught on. I guess the takeaway here is that while in conversation a lot of people say you can mix every color from the additive primaries, it's not quite true. The colors on your computer or phone screen are limited to a triangle like this. It might be slightly different, but only slightly, and it will never cover all the colors in this figure. In fact, a standard RGB that is used on many devices called sRGB is actually a bit of a smaller triangle, covering even fewer colors.
Now, I'm in the minority with this opinion, but the term complementary colors has been hijacked by artists. For over 150 years, it's been used to describe the relationship of pairs of colors in paint. Or worse, it's used to label a pair of colors that look good together. But in this lesson, I'm going to argue that the term complementary, in its strictest sense, is only applicable to additive color mixing. Pairs of colors mixed in light. Maybe I'll change your mind. Maybe I won't. So who came up with the idea of complementary colors? This guy Benjamin Thompson, Count Rumford, who, bizarrely, is the only count ever of a place in the United States. Rumford is somewhere in New Hampshire. Long story. Anyway, he's better known for his work in thermodynamics, but he also liked to play around with shadows.
Sometime in the 1790s, he noticed that if he shone a sliver of daylight onto a piece of white paper from one angle and candlelight from another angle, and then interposed a solid object, the two shadows that it cast would be quite different in hue. The candle casts a bluish shadow, and the daylight casts a yellowish shadow. The Count then got his hands on some different colored pieces of stained glass, and he continued his experiments. Well, after quite a bit of messing around, he realized that even when one light source appears colorless, like the daylight coming through the window, the shadows will always be colored, both shadows, and they'll always have very different hues. Rumford then formulated the first definition of complementary colors. Remembering Newton, he said this: "These two colors are always such that if they could be intimately mixed together, the result of that mixture would be perfect whiteness. And as whiteness results from the mixture of all the different colors in certain proportions, the two shadows may be considered as containing all the colors in their just proportions, and the color of the one shadow may with propriety be said to be the complement of the other."
Rumford was using the term complement as it's used in math, in geometry, like two complementary angles add up to 90 degrees. Two complements are two things that add up to the whole. And in the case of colors and light, the whole, according to Newton's doctrine of the 7 prismatic colors adding up to white, the whole is white.
Let's take a hue, this red, and see if we can evoke its complement. You should see in the shadow a little bit of a blue-green or cyan. So this red LED emits a spike in the spectrum, as we've said, around 635 nanometers. If I want to define its complementary wavelength, I need to find the wavelength that, if I mixed it together with 635 nanometer light at the right intensity, it would appear white, right? That's the definition of complements. But how do I figure that out? How do I figure out what wavelength that cyan light would need to be at?
Rumford says the two colors are complements if they mix to a, quote, perfect whiteness. And that remains to this day the basis for the scientific definition of complements. You can only mix two colors and get white if you're mixing additively. But to Rumford's definition, we've added an important caveat. You need to define the white. So about 100 years ago, the CIE started doing that. They started looking at the spectrum emitted by the sun in a blue sky and other light sources, and they created standard whites based on that data. This light bulb, for instance, is calibrated to the same standard white that RGB displays are built around. It's called D65. D for daylight, and 65 from 6,504 degrees Kelvin, which is the temperature you'd have to heat a black object in order for it to glow the same color as our sun scattered through our atmosphere. Whew. This light bulb is also white, but a different white, one that matches a black body burning at 2,700 degrees Kelvin. And this candle matches a black body burning at about 1,800 Kelvin. Not only can whites match different temperatures, but they can also have more of a green bias or a magenta bias. The point is, white is sort of slippery, so if you're trying to define a pair of complementary colors, you have to define white first. Now, back to my red LED. How do I find its complementary wavelength? Well, again, its dominant wavelength is about 635 nanometers, which is here. We're going to use the white point D65, which is here. And now I have two dots that I can connect, and I can find the complementary wavelength. So if I draw a line from here through the white point, out of my way, point extra, to the other end of the chromaticity diagram, I find that 480, 490, 495, about 493 nanometers is the complementary wavelength to this red given this white. That looks something like this. So now theoretically, if I mix this light with my red light, I should get something that looks like white. Rumford also says that one shadow's hue is real, but the other's is an optical illusion. And in other words, that means simultaneous contrast is responsible for the bluish tint of the candle shadow. Now, this is a clue that it's something in our vision system, not something about the light itself, that makes two colors complementary. Complements are relative to white and are related to the way we perceive contrasts against that white. And that white is something that can change based on the lighting situation or how our eyes have adapted to it.
We've now finished two sections of this course, how color works and additive mixing. So let's summarize what we've learned so far to review before we forge ahead. The sensation of color can be thought of as the output of a process that usually begins with light, or a specific illuminant with its own characteristic distribution of wavelengths. The medium that the light travels through can affect which wavelengths arrive at our eye, and in the case of a colored object, the object itself can absorb certain wavelengths and reflect others, altering the spectral composition of the light that reaches our eye. When it does reach our eye, those wavelengths are processed by a set of sensors that have evolved to detect different types of imbalances in the part of the spectrum we can see. But none of that is color per se, not until the brain processes those imbalances of sensor input and compares the signals against each other. Then, and only then, in the mind of the observer, can color be said to exist. Now, all that is necessary to know to really understand how colors can mix additively. When colors mix additively, what we're adding is light. And when we overlap different amounts of monochromatic lights, or lights that are composed of only a very narrow band of wavelengths, we see some cool stuff happen. The perceived hue of the combined monochromatic lights changes because the imbalance of wavelengths changes and our cone cells get stimulated to different degrees. Three lights, red, green, and blue, can be used to mix a wide range or gamut of colors, but depending on the lights you use, the range can be different. The CIE back in the 1930s defined the standard additive primaries as, quote, narrowband light sources of wavelength 700 nanometers, 546.1 nanometers, and 435.8 nanometers. But the RGB screens we encounter today, standard RGB for pixel displays, is defined as 612 for red, 549 for green, and 464 for blue. And OLED and different newer technologies use different primary lights. Furthermore, it's handy to think of the way red, green, and blue mix to form other colors in the form of a cube. There's 3 dimensions because there are 3 vectors, how much green, how much red, how much blue. And if you tip the cube on its side, you get a scale from dark to light, because with all 3 cone cells unstimulated at the bottom, you get black, and then various imbalances of stimulation add up to lighter and lighter colors until all 3 cones are maxed out and we perceive white. Lastly, we should remember that white is a little bit slippery. Our eyes have evolved to judge color under different illumination situations. The dark orangey light of a firelit cave, the bright bluish light of a clear sunny day. So white is relative, and the way we judge color contrasts or relationships is relative to that white. So complementary colors which are defined as a pair of colors that, when additively mixed, create white, depend on the specific white we're talking about. Okay, folks, next lesson we're going to build on what we've learned so far to discuss the mechanics of subtractive color mixing. I can't wait. Back in the 19th century, James Clerk Maxwell and Hermann von Helmholtz figured out tristimulus theory. The theory that we have three types of sensors in our eyes tuned to three different ranges of the spectrum, and that their signals are triangulated to form all color sensations in the brain. Maxwell deserves part of the credit for spreading awareness of red, green, and blue as the quote-unquote primary color sensations, or what eventually became known as the additive primaries. But how does one explain such a theory to the unsuspecting public in the 1860s? Well, Maxwell delivered a lecture in May 1861 with what I think was a genius idea for a demonstration. See, he had collaborated with a photographer, Thomas Sutton, who took 3 photographs of a plaid ribbon. Remember, the camera technology at the time was strictly black and white, but Maxwell and Sutton devised something very clever. Sutton placed a filter of red fluid over his camera for the first picture, green fluid for the second picture, and blue fluid for the third picture. This meant each photographic film was only exposed to a third of the visible spectrum, the long wavelengths, the medium wavelengths, and the short wavelengths. The result was 3 black and white photos, but with different contrasts. Not really much to look at. But at the lecture, Maxwell wanted to illustrate the trichromatic theory of color with Sutton's filtered images. Sutton printed them on a set of 3 glass plates, and Maxwell put each in front of a different projection lantern and then put a red filter, a green filter, and a blue filter over each one, making sure, of course, that they matched with the correct print. The result was a full-color reconstruction of the image of that plaid ribbon. Unfortunately, as you can see, it was kind of unimpressive. The tartan ribbon isn't exactly clear and vibrant. So rather than being a bombshell moment in the history of color theory, the lecture was kind of a meh moment, and it would take decades of research and experimentation by a variety of inventors before color photography was really sorted out. Enter Frederick Ives. In the 1890s, he invented an instrument he called the photochromoscope and a bunch of other stuff based on RGB theory. But it was also Ives who connected some important color theory dots here and figured out how to print a color photograph. He still shot his pictures with red, green, and blue filters, like Maxwell and Sutton had done 30 years before, but he realized that the paper he printed the photo on shouldn't be dyed with red, green, and blue. They should be dyed with the reverse of red, green, and blue. Why? Let's take a step back and consider how you develop a black and white photo. When you take the photo, the light comes through the lens, and the film reacts to the light. The more light falls on a given spot, the more chemical action happens on that spot, and long story short, the film gets dark in that spot. Less light, less darkening, no light, no darkening. And this means that the film, in terms of light and dark, will be flipped, a negative of the image. And when you print the photo, you flip it back, because the film becomes a filter that you project light through, and the paper you print the photo on flips the image again. Black is the opposite of white, white is the opposite of black, so the inverse of this image is this image. So Frederick Ives said, okay, well, what's the inverse of red? What's the inverse of green? What's the inverse of blue? To answer that question, you have to look at the visible spectrum. So if we have red, what's the inverse of red? Well, we take the part of the spectrum that has light and the part that doesn't have light, and we switch them, and we get a spectral profile like this. And we would see this as a color like a bluish green that's very bright and intense. Now, they didn't have that color, so to speak, in the 1890s, and we actually kind of still don't have it. Our closest approximation is cyan. The cyan that we use in printing is phthalocyanine blue. It's really a little bit too bluish, and it's not bright enough, but it's the best we got.
Now let's talk about how do you reverse green. So green looks like this, right? This is the type of spectrum that would evoke the sensation of green. If we take the part that has light and we take it away, and we take the parts that don't have light and we add it, right? In other words, if we just invert that spectrum, this is the spectrum we get. They didn't really have a name for it. Ives wanted to call it achlor. A means not, or the opposite of, and chlor, like chloroplast or chlorophyll, for green, so not green. But eventually, between him and Carl Gustav Zander and a couple other people, they sort of agreed by around 1910 that the best term for this color was magenta. Magenta was a dye and an ink that had been around since like the 1850s. The third color we need is a negative blue or reverse blue. So here is a spectrum that we would perceive as blue. We flip it and we get this spectrum, which we would see as yellow. But it's a particular type of yellow. You might call it lemon yellow. And again, Ives didn't want to just call it straight up yellow. He wanted to call the color xanth, which again comes from a Greek word having to do with like springy wood, right? So it's like a spring green type yellow. So there you go. That is the history of what Ives called the minus colors, but we have come to call today the subtractive primaries. When we place a colored filter in front of a white light, what's happening is this filter, due to the chemical properties of the dye within the film, is absorbing certain wavelengths and allowing others to pass right through. Here's that on our simplified spectrum. The white light is comprised of photons of all visible wavelengths. The filter absorbs some of them, and these are the ones that make it through. And with the simplified cone sensitivities overlaid, we see that what's happening in our L and S cones is that they're getting much more stimulation than our M cone, which is why we're seeing magenta. Now, what if I stack two filters of two different colors? Well, this is where the magic starts to happen. So here's a cyan and a magenta filter. The white light hits the cyan filter, and as Frederick Ives would say, this filter acts as a minus red. It absorbs the long wavelengths only, the ones we'd perceive as red, and allows the rest of the wavelengths to pass through. This filter has then subtracted red. Now, I stack it with the magenta filter, and we can think of the magenta filter as minus green. But it isn't subtracting the middle wavelengths from white light. Now, in front of the cyan filter, it's subtracting the middle wavelengths from a spectrum that's already missing the long wavelengths. So the cyan filter and the magenta filter has something in common. Both allow the short wavelengths to pass through, and those are the wavelengths we'd perceive as a deep violet blue. So that's the full logic behind the simple equation white minus red minus green equals blue, or really sort of blue-violet. Let's extend that to the other possible combinations with these three filters, which again Ives called the minus colors. White minus red minus blue-violet equals green. White minus green minus blue-violet equals red. And of course, white minus red minus green minus blue-violet, well, nothing's left, so it equals black. What we saw was that there wasn't much color loss, so it's sort of bending out, right? It wasn't a perfect green, but it was a very bright green. It didn't really lose very much color compared to the blue. And when we mixed these two colors, it gave me something like a red. In these scenarios, we actually maintain a lot of the color because each of these three colors represent 2/3 of the spectrum. It starts to get pretty crazy when we start looking at colors besides the three minus colors. This is a red filter. Here's what happens when I overlay it with cyan. Cyan is minus red, so it gives me black. But what happens when I overlay a red filter with a green filter? I also get black. And how about a red filter and a blue filter? Pretty much black. So not only does cyan cancel red or subtract the light down to zero, but blue and green also do a pretty good job
of subtracting it down to 0 as well. Well, let's find out if green can do the same thing. Here's green with magenta, black. Here's green with blue. Well, we get a pretty dark, dull teal color. Not quite black, but pretty close. And then, of course, we've already seen that green and red subtract down. So here's minus blue, or yellow. Pretty close to black. It's a dark gray. Here it is with red, and here it is with green. So these we've already seen, and these we've already seen. The full range of colors I'm getting is pretty dull, pretty dark. Not perfect blacks. And the ones that are complementary pairs are certainly the closest to black. So what's going on here? So let's look at it this way. Red and cyan cancel out, so we're going to draw a straight line between those. Red and green don't perfectly cancel out, but they lose brightness and chroma, so we're going to kind of curve it like this. We get a very dull, brownish something, right? The same thing's true over here. It sort of curves in. We get a very dark, purplish blue, so its line is curving in toward black but not touching it. We saw a similar thing happen between blue and green, right? It gave us a dullish teal, so it pulled in. And then, of course, if we put these opposites over each other, they close to canceled out. And these opposites close to canceled out. Maybe with a slight green bias, so we'll scooch around that way a bit. Whee! What we're seeing is an overall pattern in subtractive mixing caused by the fact that these three colors, red, green, blue, are only a third of the spectrum. Here's one more experiment worth doing. We've seen that yellow and blue cancel out, but what happens if I overlay yellow and green and yellow and red? You can see there's not much of a change. That means we're traveling along this line and ending up maybe around here, and along this line and ending up maybe around here. Now I'm going to do the same thing with my other minus colors. Here's magenta and green, magenta and blue, magenta and red. Again, not a ton of change, a slight shift here and a slight darkening here. Let's take a look at what cyan does. Cyan's not really going to change the blue. It's not going to have a huge effect on the green, maybe a slight shift in hue, and it's going to cancel the red. And there's the full pattern of next two colors, right? They're mainly just shifting in hue and not losing saturation. Let's begin with a game to review what we've learned about subtractive mixing. Assume each of these colors is the outcome of a color subtraction involving two filters. What two filters produced this blue-violet? What two filters produced this grayish near black? And what two filters produced this bright yellow? Well, you're probably thinking there's only one answer for this one, and that is cyan and magenta, right? There actually is another answer. The only other possibility is that I already had two filters that were blue-violet. Let's look at this one here. It's a near black, so you're probably thinking, well, they're probably opposite colors, and it could be any of three pairs of opposites that we've looked at. But you should also remember colors which aren't quite opposites, but which don't share any spectral overlap can also mix to black. In this case, it was cyan and red, which are complementary. Remember that Frederick Ives called this color minus red. And let's take a look at this one. Now, what two colors could possibly subtract and give me a bright yellow? If you're on your game, you know there's only one possible answer here, and that's that they're already both yellow. Okay, for the rest of this lesson, I want to go digital. Because a certain type of simulated transparency works really well as an analog for subtractive mixing and understanding how it works. That type of digital simulated transparency is called multiply. First, let's talk about why it's called multiply. Every digital color, as we've said, is a combination of different amounts of three narrowband emitters serving as additive primaries. If we tell the computer to multiply one color with another, here's what it does. It takes the amount of red in the color as a fraction of 1, takes the amount of green as a fraction of 1, the amount of blue as a fraction of 1, and it does the same thing to the RGB values of the second color. So all of the pixels in this area and all of the pixels in this area
They're really just these sets of three fractions. What happens when you multiply fractions? They get smaller. A half times a half is a quarter. So the color on one side has 2/3 red, 1/4 green, and 3/4 blue. And the color on the other side has 1/8 red, 2/3 green, and 1/4 blue. You do the math, and the resulting color will have 1/12 red, 1/6 green, and 3/16 blue. Smaller amounts of each primary light means a dimmer color, with more blue and green than red in this case, so it's like a shadowy teal. And we can confirm that result by setting these two shapes to multiply and overlapping them. Okay, so here's an important question. What happens when you multiply any number by 0? You get 0, right? So if any of these three columns in the color has a 0 in it, then no matter what the value the other color has in that column, the product will be 0. So let's take a look at this. Here's our two colors again, but I've altered them. I've raised their saturation. The purple has a 0 in the green column, and the green has zeros in the red and the blue columns. So what will the resulting color be? Well, we've got zeros in all three columns, so if I multiply them together, we get black. Like I said, I raised the saturation on these two colors, and remember, when we did that exercise from Kerpers with the paper strips, if I add my three columns across, and I have all three, red, blue, and green, they combine to white. So the amount of whiteness is actually inverse to the purity or saturation of the color. The less white, the more saturated. So if any of my columns has a 0 in it, I can't have any white component, and therefore all fully saturated colors have what? A 0 in them. That means they all have the potential to multiply to black. So let's play around and see what happens if we overlap two colors that share a side of the hexagon. You'll see that actually they're going to follow the same color mixing rules as our filters in the last video. The minus colors don't change any of the adjacent colors, and the additives, in this case the blue and the green, sort of overpower. Okay, so let's overlap some color pairs from the in-between hues, like lime and violet. Let's see what they give us. A darkish color, a sort of brown or dark red. Okay, let's overlap orange and azure. They don't give us black either. Why? There are zeros in these colors because they're fully saturated, but orange and azure both have a little bit of green in them, and while that number is getting reduced, it's not getting zeroed out. Okay, let's overlap corner colors that are across from each other. These guys are definitely going to multiply to black. Why? Because their zeros all line up in the right way. Let's pause here a second, because often in traditional color theory we learned that in subtractive mixing complementary colors cancel out. But I'm going to tell you that that's a dangerous generalization. Why? Because two colors can be complementary in hue, but if they aren't both fully saturated, and if they don't both have the zeros in the right places in their composition, they won't cancel out. As we saw, orange and azure left us a little green, lime and violet left us a little red. The other problem with this premise is that it is so often applied to how paints mix. And as we'll learn in the last section of this course, paints don't exactly mix subtractively. Building on what we discussed last time, here is a hue circuit of RGB colors, and we're going to use it to do some subtractive mixing experiments to better understand that idea that I landed on last time, that in subtractive mixing, we have to be careful about what we claim about complementary colors canceling each other out. Let's take an additive primary, green. It's set to multiply, which means it will model for me in a simplified way how subtractive mixing will work. Remember that in RGB, a pure green is a color with two zeros in it, 0 red and 0 blue. And when you multiply anything with 0, you get 0. So not only will magenta cancel to black with green, but so will this violet, and this blue, and this raspberry color, and this red. Because it doesn't matter how much is in the R column or the B column of the other color, if you multiply any 0 green color with green, you get 0, 0, 0, black. What about a non-zero green color like this azure over here? You get to keep your green but less of it, so a darker green. Same thing with this non-zero green color on this side, orange. It's got a little green in it too. So again, we're left with a darker green. You can actually chart out this pattern like this. Credit to David Briggs, by the way, who demonstrated the patterns we're going to talk about today on his website, huevaluechroma.com. What this pattern is telling us is sort of a summary of everything we just saw. All the zero green colors across the hue circuit from green all subtract to black. Colors with some green content all sort of collapse to this axis along green. If they contain 100% of green, like full saturation cyan, yellow, chartreuse, then they just collapse to full saturation green. Now, can I rotate this 120 degrees? Does it correctly show the pattern of what happens when we subtractively mix red with all these other colors? Let's find out. All the colors on this side are zero red colors, so they all subtract to black. And these non-zero red colors will collapse to different shades of red. Is the same true for the third additive primary, blue-violet? Absolutely. Just a note here that this figure is very geometrical, all straight lines and predictable angles, because we're dealing with digital RGB colors, which are all composed of just 3 numbers. With real-world colored filters, of course, things are a bit more complicated, as different materials will transmit or absorb different amounts of wavelengths across the entire visible spectrum. Back to our hue circuit. Now I want to examine with you the pattern that emerges with subtractive primaries. Let's start with yellow. We should already know that the color directly opposite will zero it out to black. Ta-da! But what about that azure? We get a dark green. The zero blue in the yellow is canceling the blue part of the azure. Same with this cyan and this sort of aqua color. Green just stays green, and chartreuse seems to stay the same too. Let's look at the other side of the circuit. The purple gives me a dull red. Magenta and raspberry are also giving me reds. Definitely sensing a pattern here. Well, here's what it looks like. This shows us that the only path through black is with blue-violet. Otherwise, whatever amount of green on this side or red on this side gets left behind means the paths we travel sort of bend out instead of in toward black, like on the additive pattern. Okay, so if I rotate this 120 degrees, we can check if cyan does the same thing. Yep, black with the complement, greens with everything on this side, dull blues with everything on the other side. The pattern holds here. How about magenta? Yep. So we can generalize and say that in subtractive mixing, additive primaries cancel more hues, all hues that contain zero of that primary. Subtractive primaries cancel only one hue, their additive complement. All other subtractions will have a bias toward one of the 2 additive primaries that are present in the subtractive primary we're talking about. Okay, now my favorite part. Here is the bizarre pattern for a color that is neither a subtractive nor an additive primary, an in-between color. We're focused on orange here. What's the only color that will cancel orange to black? Not its complement, but rather the nearest additive primary to its complement. Its additive complement, azure, will actually mix with it to make a dark green. This straight line, which is analogous to the complementary axis of a subtractive color, if that makes sense, I'm going to call it the subtractive axis, is aimed at purple. Everything on the other side of it will subtractively mix with orange to create red, its closest additive primary. This other line I'm going to call orange's additive axis. The colors connecting to the end of it will all mix with orange to a dark green, the second closest additive primary to orange, and the colors on the other side of it will approach orange in purity. Finally, this pattern is chiral. Only orange, violet, and aqua have subtractive patterns facing this way. Rose, azure, and chartreuse have subtractive patterns facing the other way. You can remember which group these in-between colors belong to based on whether they lie on each other's additive and subtractive axes. Or more simply put, they form 2 triangles. These patterns are worth getting to know, because when we get into pigment mixing, we'll see that the same basic logic influences the way paints mix as well. But there's another type of mixing we need to talk about first, because it also influences the way paints mix, and that's optical mixing. Coming up next.
Here is a close-up of a painting by Georges Seurat. You see blues, yellows, greens, reds, pinks, and when you zoom out, it all blends into green. When small areas of color are juxtaposed and the colors appear to blend in the eye, we call it optical mixing. Why does this happen? It seems to be related to our visual acuity, how much resolution our vision has, but also how our vision system, the retina, the nerve wirings, the brain, processes the information it's receiving. The first part, where colors blend because our acuity breaks down, is called visual fusion. If you recall, we said in additive mixing, what's being added is light. In our examples of additive mixing, we shined 2 or 3 monochromatic beams on the same surface so that the 2 beams of light overlap and reach our eye from the same angle. To understand what happens in optical mixing, we should modify our definition of additive mixing somewhat. What's really being added is not light per se, but how that light stimulates our cone cells. So stimulation is being added. In optical mixing, there can be an element of additive mixing caused, let's say, by the overlaps of small light cones, cones of light emission, for example, coming from RGB subpixels off a screen that are tightly packed together. In those cases, the perceived brightness of the colors will be the sum of the brightness of the different colored subpixels. Here's a bright yellow on an RGB screen. You know from a previous lesson that we can additively mix red and green to make yellow, which also adds together the brightness of the red and green. Now let's look at the red and green subpixels under the microscope. It doesn't seem to bother the yellow that there is what appears to be a black component. The blue subpixels are turned off. Yes, yellow is a little darker than white in our perception, but we don't think of yellow as containing any black. Let's take a look at pure green under the microscope. All the black area is from the fact that both the red and blue subpixels are turned off. Here's red. Both the green and blue subpixels are turned off. Again, these saturated monochromatic colors, when we zoom back out, don't appear to contain any blackness. But we go back to the yellow and we see that there's less overall darkness in the pattern. 2 subpixels are on and only 1, blue, is off. So it makes sense that yellow is apparently a brighter color on the screen than either red or green. In this case, it's because it's the result of the addition of those 2 colors. The lights from the subpixels is overlapping to stimulate our medium and long cone cells at the same time. But now, what if we enlarge the pattern a little? Quick warning, this next section of the lesson has the potential to hurt your eyes. View with caution if you have vision issues that cause contrast sensitivity. So I'll make a checkerboard, a full pixel of red and a full pixel of green alternating. If we zoom out to true pixel size now, and then take a look under the microscope at that, you see that now there are a lot more turned off subpixels surrounding my red and green dots. The red and green subpixels themselves are the same size, I'm just kind of spreading them out so that I'm reducing the amount of light that's coming from the same area of the screen. Let's compare my patch of red and green checkerboard with a patch of yellow. The checkerboard has become simply a darker yellow. Same hue, different lightness. Why? Well, the brightness of the component red and green lights has been averaged over the area rather than added. Let me explain. If we use a perceptual color picker, we see that pure RGB red has a lightness of 57. Pure green has a lightness of 84. Remember that lightness is a perceptual measure. If we average those numbers, we get about 71. If we compare a fully saturated yellow with a lightness of 71 to our checkerboard, we can see that they match in color. If you're not seeing the match, try squinting or looking at the screen from further away. So this is why another term for optical mixing, at least this type, is additive averaging. The operating principle is the same as additive mixing, but the brightness of the mixed color is averaged. Last time, we started off looking at a post-impressionist painting by Seurat. In this lesson, I want to draw your attention to the work of Carlos Cruz Diaz. This Venezuelan artist made innovative use of the viewer's perceptual system in ways that the post-impressionists could perhaps only dream about. Here we have a 1978 screen print by Cruz Diaz, where in the center area you should see a variety of hues. I see cyan, violet, magenta, orange, yellow, lime green. What do you see? Now let's look at it a little closer. We can see that the artist has only used 4 colors of ink: red, green, blue, and black. Last time we talked about visual acuity and the physical overlap of light stimulus causing the additive component of optical mixing. In this lesson, we'll further explore the other component of what's going on, the part that's going on in our retina and brain in terms of how the signals are processed. Cruz Diaz called this effect inducción cromática, or chromatic induction. A century earlier, in the 1870s, the color theorist von Bezold called the same effect assimilation, noting that the blend of colors here is similar in some way to their additive mixture. Today, scientists are still debating the neurological mechanisms that cause this perceptual effect, but Donald King has a pretty good theory. It has to do with how our brain builds perceptions from visual stimuli. He argues that if we perceive 2 parts of our visual field as belonging to a whole, our brain, in interpreting it as a whole, assigns it 1 color impression that's an average of the parts. This, by the way, is the opposite of what happens when we perceive simultaneous contrast. King says when we perceive 2 parts of our visual field as belonging to 2 separate things, this explains why our brain assigns it 2 color impressions instead of 1. And it makes those 2 color impressions more different than the actual stimuli are different. Here's an illustrative example, a little abstract composition I whipped up. The context here is encouraging our brain to perceive the yellow stripes and the blue stripes as belonging to 2 separate wholes. Those are maybe a yellow comb-like object in front of a sort of pillowy blue shape. In this second version of the design, I've taken the same exact striped region, but I've trimmed away the non-striped parts. Now there's no contour or shape information that's encouraging us to see the stripes as belonging to 2 separate overlapping objects. Instead, the stripes share a contour and shape. They belong to the same perceived object. You should see, therefore, a shade of green instead of yellow stripes on blue stripes. If you don't, try squinting. Still no? Let's use a little simultaneous contrast to intensify the effect. Now, the background of the comb and pillow design is the average hue and lightness of the 2 shapes, encouraging our brain to render their colors with even more contrast. The background of the striped single object design is now contrasting in hue, encouraging our brain to assimilate the stripes even more to emphasize their collective contrast against the background. So optical mixing isn't just a function of how light stimuli are overlapping before they reach our eye. It doesn't only happen on screens of pixels. Optical mixing is also a function of how our perceptual system interprets and groups visual information. That interpretation affects the colors we see and the way patterns blend. Let's look at one more illusion that can help illustrate how assimilation and contrast are 2 sides of the same coin. This is called the Munker-White illusion. Michael Bach has a great interactive demonstration on his website that you can play with. The green bars look different, but they are, physically speaking, all the same color stimulus. We can confirm this by sliding away the black stripes. There's a combination of perceptual effects happening here. One assimilation is telling our eyes, combine the white and the green vertically, combine the black and the green vertically. Horizontally, the eye is comparing this green to black and generating contrast to keep them different. The eye is comparing this green to white and contrasting them too.
That's my interpretation anyway. Scientists are still researching and proposing different explanations for what's going on neurologically. But also, that's the human eye. Next lesson we'll do some experiments with a color measuring instrument. We'll see what this NICS spectrophotometer does with close packed stripes of color. Last time we saw that closely packed stripes can create optical color mixing effects. This time, we're going to get those stripes way closer together. How are we going to do that? With some index cards. I've got some pink index cards that I've cut in half, and I've got some green index cards that I've cut in half. We're going to shuffle them together and look at them edge on. Once we've got the cards shuffled together, we're going to measure the resulting color with the spectrophotometer. I'm going to shuffle these with great care to make sure that they are exactly 1-to-1. Okay, so first, if we just hold this up in between our two original colors, we could see the optical blend. It's grayer. It's a slightly darker color than either of these. And if I hold it up close to the camera, you can see those pink and green stripes interspersed very closely. And the other thing that we can experiment with this is we can treat it like a flip book. If I flip through it quickly, you actually get a different type of optical blending caused by the persistence of vision. So temporal blending, right? Blending over time. If I flicker these all past your eye very quickly, the resulting color should be something like the optical blend, right? If I slow down, you see I'm just alternating between pink and green. But if I do it quickly, it all blends into that intermediary color. Now we're going to pull in the spectrophotometer. So first I'll take a measure of this pink. You can see what its spectral reflectance curve looks like. And this green. And there's its spectral reflectance curve. We can also get chromaticity coordinates. So here is that horseshoe shape that we learned about in a previous lesson. Here's where the pink is, here's where the green is. So theoretically, this optical mixture should be right on the line between those two in this chromaticity diagram. The prediction is that the color of this optical blend should be right smack in the middle of that line segment. So let's find out. If I put this on the edge here like this and take a measurement of that blended color, here's what I get. And here it is on the chromaticity diagram. So far we've seen that this color and this color averaged becomes this color, and we've mixed these like 1-to-1. There's an even ratio of each color in this mix. But now let's explore some different ratios. What about a 2-to-1 mix between these colors? Where are those going to end up on our line between pink and green on the chromaticity diagram? Well, first I have to carefully unshuffle these cards, and now I will reshuffle them with 2 pink cards to every 1 green card. All right. Obviously with 2-to-1, it's leaning more this way, but let's get a scan and see what it looks like on the chromaticity diagram. All right, here's what we got. I can also compare it visually to my 1-to-1 mix, and you can see the color difference there. All right, I'll set some of these aside, and let's go 2-to-1 the other way. Okay, here is 2-to-1 favoring green. We'll get a little scan. And let me set aside a little stack of it for comparison here. We could do more ratios, but I'm a little shuffled out. I don't think I want to look at another index card for a while. Anyway, I've probably convinced you by now that all possible ratios of optical mixture between these two colors are going to fall along a line on this chromaticity diagram. We're going to call this line an optical mixing path. On a chromaticity diagram, it's a straight line, and it's going to be pretty predictable because we're just changing the ratios of what reflective profiles are reaching our eyes and blurring together into one perception. This means that the colors have been averaged in terms of stimulus, not necessarily in terms of perception, because chromaticity diagrams are not laid out according to perception, but according to how much signal. The coordinates tell us what perceived chromaticity we can expect from the given inputs of the cone cells, but it doesn't do a good job of telling us, if we compared two coordinates, here and here, how different we'd perceive them to be. For that, you need a perceptual color space.
This is a perceptual color space. Here are my 5 scanned colors. Here are the points plotted to this perceptual color space. It's called C-LOVE, where LUV, L is lightness, U is one axis, and V is the other axis.
The U and V factors are these attempts from the 1970s to take the stimulus data and better predict how color differences might look. It's not perfect, but it's good enough for our purposes here.
The fact is the line is still pretty straight and the ratios are still pretty much where they need to be. So this isn't telling us too much because these are actually pretty low chroma colors that we mixed.
So what I think we need to do is blend two way more chromatic colors to see how their optical mixing path looks different in a chromaticity diagram versus a perceptual color space.
Here's a screaming neon green and a very vivid orange. Here it is drawing a perfectly straight line because what we're seeing here is an optical blend. So here it is in C-LOVE, and you can see that it's warped or bent that optical mixing path. What does that mean? That means that basically our perception, our brain, when it interprets the signals from our eyes, in that optical blend, it's actually lowering the chroma. It's bending it toward the neutral point somewhat.
The only reason I'm really harping on that difference, the difference between how these two different types of color diagrams represent that optical mixing path, is because I think it's going to be important to understanding what goes on when we're mixing pigments. And we're going to get into that in the next section of this course. Before we move on to integrative mixing, there's one little part of optical mixing that I want to explore with you. I mentioned this sort of flipbook effect last time, but another way to create temporal optical mixing is with spinning disks. The spinning disk experiment was sort of a mainstay of color theory in the mid-19th century. Spinning disk mixtures of color are, in fact, how people like James Clerk Maxwell, Hermann von Helmholtz, Ogden Rood, all of these scientists, artists, and educators in the mid-19th century, they all relied on this experiment to demonstrate optical mixing. And one very kind of low-rent way for you to do it at home is with a spinning top. All right, so I've cut out a round piece of watercolor paper and I am creating alternating bands of cadmium red, which is leaning slightly toward orange, as you can see, and ultramarine blue. Now, to compare the optical mixture that we're going to get out of those alternating bands, we're actually going to make an integrative mixture of the two pigments and fill in the center of the disc with that so we can compare the two colors side by side. You can see this integrative mixture is a sort of grayish purple, and I've done my best to really visually get it in between by eye. We'll see how accurate my eye is, I guess. All right, let's give it a spin. And you should see a sort of purple color.
The frame rate on the digital camera means the colors will never blend on a video as well as they do in the human eye. But the blur between the stripes captured here follows the same rules as optical mixing. If we sample it and look at those samples in a chromaticity diagram, we can see those intermediate purples follow a straight line from ultramarine to cadmium red. The physically mixed pigments, however, do not follow the same rules, and a sample of that mix will deviate from the optical mixture line, in this case being darker and closer to neutral.
But why is it darker? Same two colors, right? But now that we've actually physically blended them, the resulting color is darker than the optical mix. Why? We will get into that in a lot more depth in the next unit, but I think this is a great transition spot. What I did to try to answer this for myself was I took a blue sand and a red sand and I mingled them together, and then I added water. Let's see what happens. So first, just a caveat. I didn't have two shades of sand that were exactly like cadmium red and ultramarine blue. This red and blue, when mixed together, gave me something a lot closer to gray. But that's all right, because all I really want to do is compare the dry mixture versus the wet mixture. Now, when I mix this water in, what you're going to see is that the overall color impression of what's in this cup is going to have a darker value. What's happening in this case is that as the light hits the mixture, when it hits the mixture with water, some of that light is getting internally reflected, right? As it's bouncing around inside this goop, not all of the light is making it back out. And the internal reflection of water is just one of a number of factors that influence the way paints mix, and I'm really excited to get into them. See you there. In this video, we're going to review the 3 types of mixing we've covered so far with the help of a graphic organizer. This will set us up for a deeper understanding of integrated mixing in the next and final unit of this course.
Here's a basic additive color circle where the hue circuit goes around the perimeter, complementary colors are opposite each other, and saturation decreases as you approach the center, which is white.
Let's take a color pair and describe the additive mixing path they would trace in this simplified color space.
Red and green. If we're adding a red light and a green light, we're overlapping them and adding together their brightness. We're stimulating both the medium and the long cone cell. Our eye in this case is not perceiving added whitishness because there's no additional stimulation of the short cone cell. Brighter, not whiter. And the hue is going to be between red and green. So we would draw the additive mixing path like this and arrive at yellow. Varying the amount of each light would give us a color along that path. So mixes that are more green than red are along this line, and mixes that are more red than green are along this line. So orange is somewhere over here. Chartreuse is somewhere over here. Now, what if we add together a red light and a cyan light? Cyan is a color we see when our short cone cells and medium cone cells are both stimulated, but our long cone cells are not. Red is the inverse of that. Only the long cone is stimulated and the other 2 cones are not. So if we overlap beams of red light and cyan light, combining their brightness and stimulating all 3 cone cells, we see white. This is how complementary pairs are defined, 2 colors that additively combine to make white. And if we add red light and blue light, what's going to happen? Like with red plus green, we get combined brightness and combined stimulus of 2 out of 3 cone cells, brighter, not whiter. So the mixing path goes like this, and we get magenta. Now here's something worth noting. This same pattern is going to be true if we rotate 120 degrees. Blue is going to have these kind of mixing paths. And if we rotate it 240 degrees, green is going to have those kind of mixing paths. But interestingly, it's not true if we rotate it 60 degrees, or here, or here. Let's look at the case of magenta being added to cyan. If we overlap lights of these 2 colors, we're going to combine their brightnesses, as before. But magenta comes from a stimulation of both the short and the long cones, and cyan from both the short and the medium cones. So we're going to have all 3 cones in play, long, medium, and short, but we're doubling up on the short cone. So we won't see white because there's still going to be an imbalance favoring blue. In this case, I would draw the mixing path to look something like this, brighter and whiter, less saturated. Let's just fill out the kind of logical implication here. If we start from red, green, and blue, we're going to get mixtures that widen our gamut, which is why we call these 3 colors the additive primaries. If we started with these 3, we would not. We would be mixing very desaturated greens, desaturated reds, and desaturated blues. So cyan, magenta, and yellow are not as effective at creating a wide gamut in additive mixing.
Now let's move on to subtractive mixture. We'll start with the same two colors, red and green.
But we're going to change out the center because in subtractive mixing, all mixtures lead to black. Why? Instead of adding red and green light and getting something brighter, filters are going to subtract. Here's red, here's green. As you can see, it's opaque. No light can get through. The red filter subtracts everything but the long wavelengths, and the green filter subtracts everything but the medium wavelengths. This means that red subtracts whatever green lets go through, and green subtracts whatever red lets go through. They're mutually exclusive. So I'm going to draw subtractive mixing paths between red and green to look like this. If I mix red and cyan subtractively, I'm going to get black again. Cyan is all the medium and all the short wavelengths, but red subtracts the medium and short wavelengths. Red is minus cyan. Let's try blue. What happens again? Because they're mutually exclusive, this guy subtracts everything this one lets through, this guy subtracts everything this one lets through. We get a path that goes through black.
It's important to note that we're talking about like an idealized scenario here, because in real life, filters can have transmission profiles that overlap in ways that they're not intended to. For example, this blue filter and this green filter don't perfectly cancel out, but they both let through a little bit of light around 500 nanometers in wavelength.
As with additive mixing, this subtractive pattern can be rotated 120 degrees and 240 degrees and remain true. But it will not remain true on those in-between colors. Let's take a look at magenta now. If I mix subtractively with yellow, the yellow filter is subtracting the short wavelengths from magenta, and the magenta is subtracting the medium wavelengths from yellow. Thus, we only have long wavelengths left, and we get a mixing path like this. If I mix magenta with cyan, the same thing happens, and I get a fully saturated blue. And if I mix magenta with green, they're mutually exclusive. So they're going to mix to black or something close to it.
Now, where do optical mixtures fit in? Those color blends created by spatial or temporal juxtapositions of color. Since this type of mixing is an averaging of perceived colors, we'll change the middle of our circle for gray, which is a sort of average of all colors.
We'll start again with red and green. Optically mixing those two will average their brightness and their hue, so we'll end up with a less saturated impression of the hue between red and green, which is yellow. Depending on the type of optical mixing I'm doing, stripes, particles, spinning disks, dots of paint, the impression can vary, but generally speaking, we're going to draw a straight line between those two colors.
Yes, as we said in a previous video, they can curve a bit in different perceptual color spaces. But conceptually, it helps to think of additive averaging of color sensations as following a more predictable kind of math than subtractive mixing. Let's review all of that one last time by comparing the three types of mixing paths between two additive primaries, red and green, and then comparing that pattern to the pattern formed between two subtractive primaries, magenta and cyan.
Red to green, additive. Red to green, subtractive. Red to green, optical. Okay, now magenta to cyan, additive. Magenta to cyan, subtractive. Magenta to cyan, optical. And the difference between the optical and additive here is that the additive will add brightness, so you'll get a whiter blue, and the optical will give you a grayer blue. And finally, this pattern can be rotated 120 degrees or 240 degrees and still be true.
My hope is that this visual way of thinking about mixing paths is going to be helpful for talking about integrative mixing, because the paths that happen in integrative mixing are wild. In this final unit, the key takeaway, if you learn nothing else, is that paint mixing is not subtractive mixing, like we're often told. I'm going to use the term integrative mixing, inspired by Harold Cooper's basic law of color theory. My goal is to break down that key takeaway for you. Ultimately, the questions I want you to be able to answer are, When we mix paints, what types of color mixing are happening? Additive, subtractive, optical, and how much of each and why? And can we therefore predict with any certainty what will happen in terms of shifts in color appearance, hue, value, chroma, when we mix a given pair of pigments? Let's start with the anatomy of a paint. It is a pigment suspended in a medium or vehicle and usually applied to a substrate. When we look at a painted surface, the experience of color we get is influenced by those three components. Pigment, the substance that lends its color, is made of tiny, microscopic, solid particles. The substance has a characteristic spectral profile, a selective absorbing and reflecting of different wavelengths of light, which is what makes it valuable as a pigment. The vehicle is the substance that the pigment is mixed into, and which binds the pigment to the substrate. It's often a viscous fluid that can dry or cure into a solid. And the substrate is the surface underneath the paint, which can influence the color we perceive because some light can pass through the vehicle, reflect off the substrate, and then make it back to the eye. Given those three components, now we can define some of the variables in the mixture of pigment and vehicle. 1, pigment load. How much pigment is suspended in the vehicle? 2, pigment concentration. That's how much pigment is present in the specific application of paint. In other words, did you lay down the paint as a thin wash, or did you glob it on as a thick mass? There are other mixture variables too: viscosity, drying time, granulation, physical traits of the mixture that aren't directly related to color. So we won't get into those here. Instead, I want to move on and focus on two characteristics of the pigment particles. Characteristics that heavily affect the way the color of one pigment mixes with the color of another. First, there's the size of the pigment particles, and then there's the pigment's transparency, and those two are linked. The transparency depends on the particle size of the pigment and the thickness of the application, as well as the refractive index of the medium it's loaded in. So like watercolors, as Bruce McAvoy noted, are technically all opaque when they dry. The water evaporates, leaving just enough gum arabic to keep the pigment particles adhered in one jumbled layer on the paper. But in media like oil, acrylic, resin, pigments can be more truly transparent because the vehicle cures to a transparent solid, which the pigment particles are suspended within. This allows any transparency to the pigment itself to actually work to refract light rays that are going through it. The smallest pigment particles are maybe 30, 40, 50 times bigger than a water molecule, but usually they're much, much bigger than that. Why? Well, pigment particles usually form larger structures. They're not molecular, they're clumps or aggregates, sometimes crystals. And there can be a range of particle sizes within one pigment. In fact, a pigment can be described both in terms of its average particle size and in terms of its distribution of particle sizes. So to make all of this a bit more concrete, let's develop a scale of examples built on Bruce McAvoy's fantastic research into this topic. We'll start with the biggest pigment particles, give an example of a pigment with that average size, and then a common object for comparison. Coarse, historical, mineral pigments like azurite are the biggest. But let's start with 100 microns. Cheap burnt sienna is basically sifted dirt. Average particle size? House! 50 microns. Cobalt violet's a good example. Average particle size? Shed. That's my neighbor's shed. They just came out. 10 microns. A good example is cerulean blue. Average particle size? Subaru. It's not a cerulean blue Subaru, but it'll do. 5 microns. Viridian. Average particle size? Cozy Coupe. 1 micron. Cadmium red. Average size? Kickball. Half a micron, also known as 500 nanometers, which is a wavelength of visible light, is the average particle size of cadmium yellow, or whatever this ball is. And finally, 0.1 microns, or 100 nanometers, the average particle size of phthalocyanine blue, or this lacrosse ball. I think it's a lacrosse ball. I don't do sports. Why is all this worth knowing? Because particle size determines the light scattering properties of the pigment. In general, smaller particle size means higher tinting strength. This is why phthalos and quinacridones are so powerful in mixtures. more transparent. I find pigments with an average particle size smaller than a half micron tend to be transparent in oils, though it's not a hard and fast rule. More scattering because less surface area per particle, thus for some pigments this can mean less color intensity. If some pigments are ground too fine, they become whiter and whiter. Depends upon the mechanism of coloration. Okay, so that was a lot of information, but with those foundations, we can do some specific experiments in the next lesson and discuss how the color mixing results are influenced by the material properties of the pigments, especially particle size and transparency. Last time we talked about two related physical properties of a pigment that can affect the way it mixes: particle size and transparency. In this lesson, we're going to explore that idea with an experiment. I have here some oil paints. This is a transparent brown and an opaque brown of roughly the same hue, and I have a transparent blue and an opaque blue of roughly the same hue. Watch what happens when I mix the opaque blue and opaque brown. Traditional color theory is pretty comfortable with the result that we're getting here, right? The traditional color wheel tells us, well, if colors are opposite in hue, they will cancel out. Brown is a dull orange and blue and orange are opposites, so I'm not surprised to get a dark gray. Now I want you to see what happens when I mix the transparent blue and transparent brown. I get this dark, gorgeous forest green. After I swatch it out here, I'm actually going to use a paper towel to pull up some of the paint so we can judge these in terms of their undertone as well as their mass tone. You see that my opaque mix has a clear purple bias and my transparent mix has a green bias. Well, the question is why, right? The two pairs of paints I started with don't really have that different of an appearance in mass tone. But let's compare the pigment's respective mass tones and undertones. Mass tone is the color a pigment shows when it's in a big fat glob, where none of the substrate is showing through. The undertone is the color of the pigment in a thin layer when the substrate is allowed to show through. Here I've diluted the paint with a little bit of walnut oil. So what you should see here is that Cobalt Blue Deep, which is an opaque pigment, has a mass tone and an undertone that are roughly the same in hue. Obviously the undertone is lighter in value, but it isn't greener or bluer than the mass tone, not significantly. However, with the phthalo blue, you should notice that the mass tone is, like our Cobalt Blue Deep, a somewhat purple blue, closer to ultramarine than it is to cerulean, and it's very dark. And then the undertone is not only lighter, but is also closer to cyan. In other words, it's a greener blue. I'm going to pull some up with that paper towel to really show you the difference here in those undertones, right? The undertone of Cobalt Deep is definitely purpler, and the undertone of phthalo is definitely greener. Let's compare the opaque and transparent browns as well. Burnt sienna in mass tone is a little lighter in value than our transparent pigment, quinacridone burnt orange. Let's examine how they each appear in undertone as well. You can see here the sienna, burnt sienna, with a little walnut oil mixed in. Feels a little like warmer. It feels more like a red orange than a brown. So that means it's gone up in chroma a bit, but it hasn't really shifted in hue. Here is our quinacridone burnt orange. Now when I thin it out with walnut oil, it should actually feel a little more like a yellow orange, right? It's shifting in hue toward yellow. We're going to pull out our additive/subtractive/optical color wheel that we used in the review lesson to see if our knowledge from all the previous lessons helps us to understand what's happening with these pigments. First, we got to figure out where do we put our pigments. We're going to start with our phthalo, which in mass tone we're going to say is somewhere around here. I'm going to label that PB15. That's the color index code for phthalo blue. In undertone, it actually shifted towards cyan. It also became lighter, and it also became a little bit more chromatic. So I'm actually going to put it here, closer to the edge of the circle to indicate that it's higher in chroma, and closer to cyan to indicate that it's shifted in hue. What about our Cobalt Blue Deep? That's PB74. I'm going to put it, I don't know, like here. In undertone, we saw that it was lighter, which is expected, but not really shifting significantly in hue. So I'm just going to leave it as a dot right there.
Okay, our browns are up here. This is our burnt sienna, PBR7, and this is our quinacridone burnt orange, PO48. In mass tone it is darker, but it is more chromatic. In undertone, we saw that this guy shifted this way, so I'm going to do a little dotted line showing that in undertone he's more chromatic and he's closer to yellow. This guy maybe in undertone is something more like just more chromatic, but about the same hue. The question is, when I am mixing them, what paths are they tracing? But because our transparent pigments have such different colors in terms of their mass tone and undertone, the question really is which version of our transparent brown and our transparent blue should we use to predict their mixtures? Well, when we mix a paint with anything, including another color, what we're doing is thinning it out and averaging it with the physical properties of that other color, including the absorption and scattering ability of its pigment particles. That means we should base our mix predictions on the paint's undertones. With transparent pigments, this is the reference point for the mixing path. I'm going to bring back this overlay that is a little bit different from the overlay that we had going in the review lesson, but what it's showing you is a primary having outward bending mixing paths. Right when we mix yellow and magenta, we get a pretty decently high chroma red, and our subtractive secondaries, which are also our additive primaries, red, green, and blue, are actually going to bend in and cancel. So look at my PB74. It's pretty close to this subtractive secondary color, which means anything that I mix with it, including one of these oranges over here, I can predict that it is going to lose chroma and tend toward black, which is what we saw. My mass tone of my phthalo isn't that far off, but remember, I want to use the undertone to predict its mixture. So let me actually rotate this, because cyan is a primary in subtractive mixing. So the fact that mixing this with this actually did something like this and gave me a forest green matches with the prediction of subtractive mixing, because this guy and this guy are pretty close. They're at least slightly closer to subtractive primaries than my opaque pigments, which are more following a line like this because they're closer to my subtractive secondaries. Okay, we're going to build on the last lesson by comparing some more paint mixtures. I have a transparent green, phthalo green yellow shade, PG36, and I'm going to mix in PR207, which is a transparent quinacridone red. You can see it's a very dark mixture. It's sort of a neutral brownish green. Now let's do my opaque paints. There's actually no opaque, highly chromatic middle green pigment, so I had to make a mix. So this is bismuth yellow and cobalt teal mixed together to make that. And I'm going to mix cadmium red into it to get this sort of neutral that's got a warm cast. In hue, it's probably a yellow-orange, but you can see it's much higher in value, and it's still pretty dull. As I was looking at these, I wanted to see if I could get that transparent mixture to match the opaque one in hue a little better. So I'm going to thin it out here and actually add in some more of the quinacridone red to see if we can get, you know, a somewhat similar dull yellow or yellow-orange. Now we'll turn our attention to a pair of yellow and purple pigments. This is PY128 and quinacridone purple PV55. You can see I get actually kind of like a blood red color, pretty chromatic. And the funny thing about this is it actually has a green undertone. Now we'll mix together our bismuth yellow and some cobalt violet, which is, you know, semi-opaque. And you can see I get kind of a dull flesh tone, but it's, I would say, much more chromatic than the red-green mixture we got.
The first thing to notice is that in both cases, the opaque mixture was lighter, was higher in value than the transparent mixture. This is because an opaque mixture is going to be able to diffusely scatter light better than a transparent mixture, which is actually absorbing more of the light than the opaque mixture. It can also scatter some light, which is why we still see color, but it's darker because more of the light is penetrating into the transparent layers of medium and pigment and getting sort of trapped and absorbed in there. So the transparent mixes in both cases are darker. The other thing to notice is that the hues that we're dealing with are also behaving differently. When I mix the yellow and the purple, the yellow is a subtractive primary. The purple is sort of close to magenta, but it's not quite on it. The green and the red that I chose are both pretty close to additive primaries, which, as we've seen in subtractive mixture, both tend to lose more chroma. Let's go back to the chart to try to make sense of all of this.
In this version of our chart, I've got the subtractive primaries marked with a minus and the additive primaries marked with a plus. I've got these light blue lines, which are telling me subtractive mixing lines. So a subtractive mixing line between two subtractive primaries bends outward, meaning it tends to maintain chroma or colorfulness, whereas a subtractive mixture between two additive primaries will bend inward and lose chroma and tend toward black. The dotted lines are straight lines between these six colors that indicate the expected mixing path if we're going optically, right? So it doesn't matter if my colors are additive or subtractive primaries in optical mixing. I'm just taking the visual average, so all those lines are going to be straight. So what we saw in the paint mixing demonstration just now was this. If I take these two colors and mix them with transparent pigments, I'm actually going to get something closer to a subtractive mixing path. But if I mix them in opaque pigments, I get something that is going to be more like averaging their value or their lightness. But more importantly, it's got a little bit more colorfulness to it because it's visually averaging more than it's subtracting. But in both cases, I'm actually somewhere in between. So let's say I'm dealing with semi-transparent pigments. I might be doing something like this. The point is there's a range of possible paths between these two colors that are somewhere between subtractive and optical. And what we saw with my yellow and purple mixes was something similar, except doing this, right? If I am mixing the transparent ones, I'm going to get a more punchy red, a slightly better chroma than expected. And if I'm mixing the opaque ones, I'm getting something more like an optical mixture. Again, maybe I have semi-transparent pigments and maybe that does something like this. But what I'm showing here is that all of the possible paint mixing paths are probably going to be somewhere in between these two lines.
Now there's two really smart follow-up questions here, which will lead us into our next two lessons. Number one is, what if the color I'm mixing isn't a subtractive or additive primary? What if it's in between? What if it's a color like violet or orange? The other follow-up question to this is, what if the spectral reflectance profile of the pigment I'm dealing with is a little wonky, and how might that affect the predictions on this chart? We've looked a little at the importance of whether a paint is transparent or opaque, and in this lesson we're going to continue to look at the impact of subtractive mixing paths on paint mixing. As we explored way back in lesson 12 and demonstrated again on this chart, subtractive mixing paths have a specific pattern. Cyan, yellow, and magenta, as colors that result from the stimulation of 2 out of 3 cone cells, have mixing paths that bend outward, meaning they maintain more chroma than optical mixtures of the same colors, which are straight lines in a chromaticity diagram. Red, green, and blue, on the other hand, as colors that result from the stimulation of only 1 out of 3 cone cells, have subtractive mixing paths that bend inward, meaning they lose chroma and tend toward black. So the question becomes, in subtractive mixing, what happens when we mix a hue that's between a subtractive and additive primary? We briefly discussed this too in lesson 12, but now we're going to go more in depth. For paint mixing, understanding the mixing paths of in-between hues becomes important because actually many common artist pigments are in-between colors.
For an in-between color, we will take this, rose. It's actually pretty close to the hue of quinacridone magenta, which is a major choice for a mixing primary for a lot of people. And I guess the question is, all right, so if I know like this guy as a subtractive primary is bending out and this guy as an additive primary is bending in, What does that mean this guy's doing? Well, in a couple specific cases, it means it is kind of going more in a straight line. Here and here. And it forms a triad with these other colors. I'll call this one chartreuse, and I'll call this one azure, sort of a middle blue. Bending in and bending out cancel, and we get this straight line. But from there it gets weirder. Visually, this sea green color is the complement of rose, right? If I were mixing them in light, they would cancel out. If I were optically mixing them, they would cancel out. If I'm talking about subtractive mixing and what wavelengths are being let through, the fact is this guy lets through a little bit of blue light, and this guy lets through a little bit of blue light. So even though they're visually complements, what's going to happen is their mixing path is going to bend toward blue. That means that actually this guy is the mixing complement to rose. This sort of subtractive behavior of paths bending outward continues over here. So if I mix quinacridone magenta with a yellow, I do get kind of a halfway decent red, halfway decent orange. And if I mix it with reds and oranges, I don't really lose too much chroma, right? So what about this other straight line here? This is where it gets really interesting because now it's going to actually act more like its closest additive primary. It's actually going to bend inward on this side. It's going to lose chroma more than expected in mixtures with blue violets and violets. This mixing pattern I like to think of as being right-handed. It is got like a thumb here that points to one of its triad where it kind of mixes a straight path, and on the other side of that thumb it's mixing as though it were an additive primary. The middle finger I think of as its other axis here that's acting as its subtractive axis to chartreuse, and the pointer finger is kind of pointing to its mixing complement, the color that it's going to cancel with. Okay, I think of it in terms of being a hand. The other reason I think of it as a hand is because it helps me remember that these patterns are chiral, meaning they are handed. Some of them are right-handed and some of them are left-handed. So rose, chartreuse, and azure, the three members of that triad, are all right-handed. If I flip this acetate over, I can look at the other three. I've got sea green, orange, and violet. These guys are left-handed, right? So this guy's thumb with his additive behavior is over here. You know, you can't really get decent cyans or turquoises mixing blue and green pigments. Now let's look at sea green's pointer finger. What's the color that is going to cancel to black? Not its visual opposite, but red. So cadmium red and like viridian would actually line up with this, and that's why Impressionist painters in the 1800s could claim that these two colors were acting like opposites, and that's one reason that the traditional artist's color wheel has red and green opposite each other instead of green and magenta. So again, if I turn it this way and I look at violet, violet's going to act left-handed, and orange is going to act left-handed. So let's talk about a few more examples of popular or common pigments that are in between colors. Cerulean is near azure. Cadmium orange is on a lot of people's palettes. That's right by that chiral left-handed orange color. I mentioned viridian, but phthalo green is also a green that behaves like this sea green. It gives us really nice mixes with yellow, really vibrant yellow greens, but it doesn't do too much for these mixes. So that chiral pattern is really weird, but I want to show you something I discovered which helped me to understand why it is the way it is. Okay, check this out. This is the mixing path pattern for an additive primary. This is the mixing path pattern for a subtractive primary, like we're all bending out, right? Watch what happens as I move this window and kind of slide it around. Now I'm back to that additive primary pattern. Now I'm back to that subtractive primary pattern. But look, if I go in between, I've got something like what would happen for violet or orange or azure. I've got some lines bending in. I've got a straight line forming a triangle. And I've got some lines bending out on the other side. So here's the key insight. We're changing whatever the dominant wavelength is of that hue, moving it around within our visual space, and so we're just moving the window of how that color is going to behave when we mix it subtractively. In this lesson, we'll get into full spectrum analysis of pigment mixtures. I want to start this discussion with a question that's sort of pivotal in color theory. The diverging way color theorists have chosen to answer it, I believe, is the reason for the ongoing division between traditional and science-based color theory. And that question is this: if yellow and blue are opposites, as science-based color theory claims, then how come when I mix them in paint, I get green? Science says these two colors are complements. In additive mixing, these hues mix to white. An optical mixture should therefore give me gray. And subtracting these complements should leave me with black. But these subtractive filters, I get this dark green with them. And when I mix the same colors as paints, I get a similar dark, dullish green. Why? Well, there's one thing we haven't fully considered yet. All of this perfect subtractive mixing we simulated on the computer in lesson 12, those were these perfectly geometrical lines. They perfectly canceled to black because those colors are being defined in a color space with only 3 vectors: how much red pixel, how much green pixel, how much blue pixel. In other words, we were mixing 3 monochromatic lights, like we were when we mixed on my additive color demonstrator. These colors then were narrowband single spikes in the spectrum. But filters and paints, not so much. These filter paddles from Rainbow Symphony actually come with a set of charts of the spectral transmission for each of the 6 filters. Here's our yellow filter, and here's our blue filter. You can see that these are not simple spikes in the visible spectrum, but these complex functions of transmission versus wavelength over the entire visible spectrum from 400 to 700 nanometers. Check this out. It's an LED array. Each of the LEDs gives a narrowband spike of light emission at the designated wavelength here on the rod. I'll turn it on for you. You can see you get sort of a nice visual representation of the visible spectrum from deep red all the way down to near ultraviolet. So with this array, we can put these transmission profiles to the test. Look at this blue chart again. You can see the wavelengths that are getting blocked are about 550 nanometers end up, with a little bit of near-infrared light coming through. We can confirm this on the LED array. Watch this. Okay, violet, blue, turquoise, green, and then look what happens. As soon as I get up into the yellow, orange, red wavelengths, they start to disappear. And then, I don't know if you can see this, but up near the top, there's a tiny bit of near-infrared light coming through. All right, let's take a look at our yellow filter. It looks like nothing under 450 nanometers should come through. This guy should be just about blocked out. 470, we might get a little squeak. 505, we should see about 30% of that. 525, we should see most of that coming through. And everything else should be barely impeded. I get 80% transmission. So let's see what happens. You can see a lot of that red, orange, yellow is coming through. I get down to green. It's still passing through pretty well. And my blues are a little bit dimmed. But this isn't super dramatic, right? To get a better effect, we'll try it with a stack of 3 yellow filters. So here we go. Red, orange, yellow. Those are all coming through nice and strong. Not really changing much. I get down into my greens. You can see exactly where it drops off. Right? My 505 nanometer turquoise LED is mostly shut off. And then look, my short wavelength guys are basically completely blocked out. So here's the crux of the matter. 500 to 550 is being partially let through by yellow and partially let through by blue, just a little bit. So because there's an overlap in transmission, what I should expect to see is this very dark greenish color. And let's see here. I've got 525 nanometers here and 505 nanometers here. Those are right in that overlap range. So theoretically, this should block out everything above it and let a little bit of that through. It's also letting through a little bit of my blue light, probably because this yellow filter isn't a super efficient blocker, right? It's not blocking those wavelengths quite as fully as this chart claims it is. But enough lights and filters. Let's get back to paint. Why is that also giving me this dull green. Okay, as you can see, I've prepared a number of gradients. This one is ultramarine blue mixed with bismuth yellow. We're going to take a scan of the ultramarine blue. This is its spectral reflectance profile. And we'll take a scan of bismuth yellow. That's the profile of that pigment. What we're going to do now is scan a few stops along this path to see how that function of reflectance over wavelength changes as I mix different ratios of these two pigments. There's ultramarine blue again. As I get to the middle, you see this spike around 500 nanometers, right? And then we move past that. Very similar to the overlap in transmission with my filters. There you go. As a transparent pigment, ultramarine blue has more absorption, right? And as an opaque pigment, bismuth yellow has more scattering. And so that's one reason that the mix gets lighter and lighter in value as it moves toward yellow. But also, different absorption and scattering factors exist at every wavelength along the visible spectrum for each pigment. And so you're seeing some funny shapes going on in there, right? As that peak sort of moves across through green and into yellow, right? There's sort of this bend, like the long wavelengths, that sort of has to like bump out. And that funky shift of shape is a result of the scattering and absorption coefficients for each pigment as the ratio changes. It's pretty complex stuff, but I think hopefully at least you now have an answer to that question of why, even though we have two colors that visually are complementary, we have two substances that when we mix them do not behave as expected, but give us this shifting green through the spectrum as that dominant wavelength sort of moves over. So we've come to the end of the color mixing course. We've covered the mechanics of color vision, additive, subtractive, and optical mixture, as well as the way paints mix. In this video, we're going to do a sort of informal final exam, an interactive review. I've designed these 15 questions to be somewhat challenging so that you can identify for yourself the sections of the course you might want to review for a better understanding. In this review, I'll pose a question, then invite you to pause the video so you can work out your answer. Then I'll give the answer. For more in-depth explanations, use the provided study guide. Are you ready? True or false? Different wavelengths of light in the visible spectrum have different hues. Pause. The answer is false. Color is a perception that comes from the cone cell sensors in our eyes, comparing their signals and encoding them so we see different imbalances of wavelength across the spectrum. Which of the following affect color perception? The illuminant or light source, the properties of the object reflecting the light, the viewing context, or the observer? Pause. The answer is all of the above. Color perception is a result of a complex combination of factors. Why do we call the mixing of colored lights additive mixing? Pause. Because we are adding stimulus. The result of an additive color mixture is brighter than the two starting colors because more light is being reflected or emitted from the same location. What do these three curves on this graphic represent? Pause. This graphic shows the ranges of sensitivity across the spectrum of the three types of cone cells in the typical human retina. This is a spectral emission profile. Again, the shorter wavelengths are to the left and the longer wavelengths are to the right. Now, though, the vertical scale is how much light is being emitted. If I see an object that's emitting a spectral profile like this, which of my three cone cells is going to be the most stimulated? And what color would it therefore look like? Pause. The S cone will be the most stimulated. This spectral profile would probably therefore look like a shade of blue. Now this is a spectral reflectance chart of a pigment. Can you estimate the hue of this pigment? Pause. The answer is a vibrant yellow. That means the light reaching our eye will stimulate the M and L cones with very little stimulation to the S cone. Why did Frederick Ives call cyan, magenta, and yellow the minus colors? Pause. Because they could be defined by which of the three additive primaries they absorbed. Red is stimulated by the long wavelengths, thus minus red, or cyan, was only not the long wavelengths, or said another way, cyan is only the medium and short wavelengths. Theoretically, yellow and blue-violet should subtractively mix to black. Why then do I see a dull teal green? Pause. Because both of these filters allow a little bit of light of medium wavelength to pass through. The resulting pass-through is picked up by the M cone and perceived as a dark green. If the complementary colors red and cyan are supposed to cancel to black, why do red and blue also cancel to black? Pause. Because those two filters don't share any transmission in the spectrum. A green, cyan, blue, or violet filter, any of those that don't allow long wavelengths to pass through, will subtract to black with a red filter, since red only allows long wavelengths to pass through. Additive mixtures get brighter, subtractive mixtures get darker. What happens with optical mixtures? Pause. Two colors mixed optically will average their lightness. True or false? Pigments with larger particle sizes tend to be opaque and have weak tinting strength in mixtures. Pause. This is true. Larger particles give light less opportunity to penetrate the paint film and bounce back off the substrate. These pigments also have weaker tinting strength in mixtures because their particles can't get into all the nooks and crannies. When mixing paints, do transparent pigments behave more subtractively or optically? Pause. Subtractively, because transparent pigments can create thin layers of color which allows some light to pass through, hit the substrate, and bounce back to the eye. This means they can act more like filters, absorbing some wavelengths and allowing others to transmit. Okay, ready for a few really challenging questions? I'm going to throw these in here, but not give you the answers. Why? I really want you to work these out yourself. I think you can. But if you can't, all that means is it's an invitation to review the material and maybe ask follow-up questions in the Discord if you need help. Okay, ready? How are optical assimilation and simultaneous contrast related? In subtractive mixing, additive primaries have introverted mixing paths and subtractive primaries have extroverted mixing paths. Why do in-between colors like orange have chiral mixing paths? Last question. When mixing transparent paints, why should you predict their mixture results based on undertone and not on mass tone? Okay, that's it. We've officially reached the end of the color mixing course. Thank you so much for being here, for putting your faith in me. If you would like a professional development certificate, please just email me at peter.donahue@gmail.com with certificate request in the subject line. I'll make you a 3-hour certificate that you can submit to your institution of choice. All right, I think that's about it.